this is what we're going to do. The main part of today is going to be, we're going to do a section 7-8 called improper integrals, which is fine. But before we get to do that, there are two other sections that you might want to know what's happened to them. So let's show you them. First section is section 7.5. It's called Strategies for Integration, optional. And I've put this one up and I've gave it a whole load of 0 points, so you can do it if you want for practice. And essentially what this section does is it gives you a whole load of random questions to do with integration. So it's not that you don't know how to do any of them. The biggest test is going to be, do you know which method is the right method? So let me make this a little bit bigger and we'll start and go through some. Now, the techniques that you really will be using mostly are U-subs, integration by parts, and X-subs, right? So let's look at question 1. Hopefully that's one you can see. It's a U-sub, but maybe not the most obvious one, or maybe it is the obvious one, I don't know. What would be the U-sub you should use in question 1? Anybody?
Eight minus sin x.
Correct, that's the right one. In question 2, what method will you use to do question 2? Anybody?
Does it seem like integration by parts?
It is. What made you think that? Because it is the right thing.
I saw two functions and it just seemed like the more logical path. I mean, there was no sine, cosine, but it just seemed the more logical path.
Okay, that's true. Now, if you want to do integration by parts, don't you have to pick an f of t and a g of t?
Yes, for this one I would pick natural log of y as the f of as the f function, only because it's easier to integrate.
Yeah. Well, differentiate actually, but yes.
Or sorry, yeah, differentiate.
I knew what you meant. Right. What are you going to do in question 3? Anybody again? Okay, I'll start. It's a U-sub. What's U-sub would you use?
Cosine.
Correct. Now, if you do that, you're going to be left with a sine squared x, like a little orphan. But can't you turn sine squared x into 1 minus cos squared, which becomes 1 minus u squared, and off you go. 4 is a stinker. It is a U-sub, but it is not t to the 4 plus 5. And it's not even the U-sub t to the 4, which would probably be my next best guess. What is the U-sub you will use in question 4?
T squared?
You nailed it, t squared. Trust me, it ends up being an ugly inverse tan. What would you use in question 7? So U-sub again. Anybody? What would you use? We did a whole section, well, half a section that was devoted just to these guys.
Cosine.
Right, I hear cosine t. That would be the one I would choose. You could actually do sine t, but it would take you longer. Well, actually, I take that back. You can only do cosine. The sine wouldn't work. Do you recognize question 9 as being an X sub? Right, we only did 7 of those darn things. The square root of 1 minus x squared is the clue. And you'd have to go check in the tables, but it's actually x equals sine theta that you would use. 11 is a trick question. I'll say it again. Question 11 is a trick question. What's the answer? If you integrate 6e squared, what would you get as your antiderivative?
Would it be 3e squared?
No. I can understand why you would think that, but no.
Would it be like 6e squared x?
Yes. That's what makes it a trick question. Isn't that just a weird number? And when you integrate weird numbers, isn't the answer weird number x? So it's not an integration by parts or some kind of weird derivative or whatever. It is what it is. Okay, if you were doing question 13, I'm telling you it's a u sub. Who do you think the u sub's going to be?
It would just be ln x, right?
You nailed it. It
All right.
actually comes out quite nice. 14 looks ugly, which it is. What would the u sub be in 14?
One plus the square root of x.
Yeah, and just trust the math. It's a heck of a long question, but that's what you would do at the start. What would you do in 15? I don't know how good your screens are. See if I can make it even bigger. There. What would you do in 15? Anybody?
Me.
Last chance. There's not a lot of choices, agreed? There's not an awful lot of choices. It's a u sub. So who? Last chance.
Is it just the whole denominator?
Correct. 8 plus e is x. You have to trust the math because you'll have to fight through that, but it does come out. You'll end up with something ridiculous like 8 minus u over u or something, right? But, you know, that'll sort itself out. 16 is a u sub. Remember when it's tans and secants, don't you just pick one secant or one tan? Right? So the u sub is secant theta or the u sub is tan theta. So there, I've gave you two choices, but only one of them is a good one. So who do you
I think
pick?
it would be secant squared, right?
Mm.
No. Jeez.
You
Louise.
only pick a single power in these cases. So it's u equals secant theta on its own, or u equals tan theta on its own. No powers of those. That's very, very, very rarely ever going to help you. So secant or tan, that's your choices.
Tan?
Correct. I guess, or is there a reason?
Well, I think, if I remember right, the derivative of tan is secant squared.
Yeah, and that just
And
turns
then-
into the integral of u squared. That's exactly why. Yep. Any ideas what you might do to 17? This is definitely not obvious. Don't even, you know, if you get this, you deserve a prize. Not that I'll give you one, but you deserve one. It's a U sub. And not even an obvious U sub, in my opinion. But nonetheless, it's a U sub.
Secant?
I would do,
I had secant. Was that your choice going to be, Evan, before I interrupted you? It's a
Yeah.
good choice because when you differentiate a secant, that secant tan in the top disappears. This turns into a 2 on the top and a u squared minus u on the bottom du. Now, u squared minus u is no good, but it factors out as a u brackets u minus 2, and so it then ends up being integration by parts. So that's our long question. A u sub just to get an integration by parts. 18's a u sub. Who is it?
+81 plus e to the x.
Yep. You have other stuff to do later, but yep, that's it. What do you think the u sub in 20 is going to be?
Square root of x.
Yep, works out quite well, actually. Last one. What do you think the u sub's going to be here? And I am going to, before I, well, you might already want to tell me the answer, but before we get to that point, I have told you that when you've got tans and secants, only pick one. Very, very, very rarely do you pick a sine squared or a tan squared or a whatever, right? But that's only very, very, very rarely. Just now and again, that's exactly what you have to pick. So what's the u sub that's going to work with 21? And even after saying that, it's not obvious what the u sub is.
Is it cosine x?
Well, I've kind of indicated that it should be bigger than that, but you're right about the cosine part. But more than just one cosine.
Cosine squared.
Yeah. And if you differentiate cosine squared, you'll get something like -2 sine x cosine x, which, by the way, is what sine 2x is. So that thing there just turns into -3/2 1 plus u squared. So it ends up being an inverse tan. And that is the end of those questions. So that is optional. You can choose to do them. You can choose to do all of them or some of them, whatever you feel comfortable about. But it is optional. Okay, so what was the other section? Well, the other section was one where it was 7.6 and it's using tables. And I'll put an optional version of that up and you can practice that as well. So if you choose to do one of those guys and you complete it to the end, you will tell me and I will check that you've done it, and you will get your 2% extra credit for those who haven't already got a 2% extra credit. Now, you can only get at most 2% extra credit. So if you've already got one, you're just doing it because it's good for you, right? But if you haven't got your 2% extra credit and you want an opportunity to do so, do one of those optional homeworks, right? And shoot me an email saying, I have done optional homework, and tell me which one and I'll check it. And if you have in fact done it, I'll give you your 2%. Okay, so it's still optional, but if you do it, I'll give you 2%. So does that make it optional anymore? Well, you can choose not to do it and your grade won't change. So I guess in that sense it is. Right, Well, let's get that guy out of the way. Let's start 7-8. We are going to be looking at what's called improper integrals. Improper integrals are integrals with infinities involved in them. That's what makes them improper. And we are going to look at least today, how to integrate fractions, because almost every one of them is a fraction question. I'm going to start with a very simple one, that one. And it's an improper integral. Actually, if there is an integral in one of the limits of integration, they're called type 2. So an improper integral of type 2 has at least one infinity here or here. Now, a lot of people falsely think that if you find an area under a curve, even if it's this curve here, and if I draw this curve, it looks something like this. And you start at 1, and you go to infinity, and you find the area under this curve, that this area is bound to be infinity. Right? But that's actually not always true. It is possible to have an area under a curve, even although this curve continues in the right forever, for the area under the curve to be a finite number. And although that conceptually might seem weird to you, it does in fact happen. And so you have to just accept that it happens, or intuitively it might make sense to you. Because can you notice that at the bottom here, doesn't it get very tiny, very skinny, almost no area at all? So if it gets, low very quickly, this can have an answer. If it has a numerical answer, we will say that it converges to whatever the number is. So we might say it converges to 40, it converges to 3/7. That's how you would say it. If, however, the answer to the integral is infinity, or for some other reason it doesn't exist, then you just say diverges. So when you're doing your homework question, your answers are almost always going to be, does this thing converge or diverge? And your job is to find out which. So I'm going to show you the process at how we find these integrals and if they converge to a number or not. And it works something like this. We turn it into a limit. And it's typical to use the letter T. Don't know why, but they like it. Now, does that logically make sense that the integral from 1 to infinity of this guy is the same thing as the integral from 1 to t of this guy, and then you make t go infinitely large? Would you agree that they're essentially the same thing written in two different formats? Does it? So far, so good. Now, we are going to calculate, forget this, we are going to calculate this in the usual way. And then once we've figured out what the answer is, and this answer is bound to have t's in it because of that, once we find out what this is, then we'll find out what happens to this expression as t goes infinite. So here goes. It's going to be the limit as t tends to infinity. I would change this guy into a negative power. Why did I change this fraction into a negative power? What was my reasoning?
So we can do the power rule.
Exactly. And isn't the power rule add 1 to the power and divide by the new power? And then I would evaluate it at x equals 1 to x equals t. And I suggest very strongly that you do style points on these questions. So rewrite this guy like that. Okay. So that's the antiderivative evaluated at these two things. Let's see what we get then. If you plug in t, you get negative 10 over t. Take away, plug in 1. Take away negative 10 over 1. Take away makes it a plus. You end up with plus 10. Are you happy with t gives you this, and take away that gets you plus 10? So you find the integral. Here it is here. It has t's in it, which we predicted it would have. And the last final step is to find the limit as t tends to infinity of that. Now, when you do limits, there are a number of techniques that you found from Calc 1. One of the techniques I call, I call it brute force. So I'm coming back to that question, but let's do a little side issue on what kind of things might happen when you get to this last step. Right, in brute force, what you do is you take your expression and you plug infinity in, and you should be, in some circumstances anyway, to be able to tell what's going to happen. So I'll give you an example of that. 10 over t cubed plus 4 over t plus 7. Now, if I did the limit as t tends to infinity of this, I would get 10 over infinity cubed, which is just infinity, plus 4 over infinity, plus a 7. Agreed? And here's the clever part. What's 10 over an infinitely large number essentially the same value as?
0.
And would you agree that 4 over it is also 0? And the net result here is that this thing has a limit of 7. Can you remember that technique where you can just plug infinity in and get an answer? It typically works really well when you've powers of t on the bottom, but you can do it with more awkward things. So let me try some more awkward things. Suppose I did 1 over 3 e to the t plus 1 over the square root of t plus 1, right? Just randomly, yeah. Now, in this case, isn't e to the power of infinity infinity? And isn't 3 lots of infinity still infinity? You know, infinity is a funny kind of calculation, right? Squaring infinity still gets you an infinity, right? It doesn't get you some other different kind. Now, what about this fella? Well, let's think it through. If this is infinity, isn't infinity add 1 still infinite? And what would the square root of infinity get you? You may have said it, but didn't hear it. Square root of infinity.
Just infinity.
Yeah. And so in this case, wouldn't the answer be 0? So we call that brute force. At least that's what I call it. There's a second technique that you sometimes have to use. And this happens when you get things like 3t squared plus t on the top and 2t squared, say, plus 7 on the bottom. It's not a good idea to do brute force on this question, because if you do the calculation on top, you basically get 2 infinities added and an infinity adds 7. So what you get is an infinity over an infinity. And no, that is not 1. Brute force fails in these questions, right? In fact, if you ever get infinity over infinity, we even have a name for that. Called indeterminate form. So the technique that we're going to use for questions that look like these, I don't know who you got for Calc 1, so they may have tackled this differently, but this is how I do it. You divide the top and bottom by a power of t. So you divide the top and bottom by t, or t squared, or t cubed. So how do you decide what it is? Would you agree that the biggest power of t on the top is t squared? And would you agree that the biggest power of t on the bottom is t squared? So in this case, I have no choice. Now what's going to happen when I do that then is I'm going to get, that guy gets you 3, Divide him by t squared, you get 1 over t. Divide him by t squared, you get 2. And divide him by t squared, you get that. And now I can do brute force. And 3 plus nothing, 2 plus nothing, there's your answer, it's 3/2. Now you can also use this, and here's another situation where it's going to get used. Now you're still going to divide the top and bottom. And I suggest that when you have a situation where the powers on top are different, as they are here, that you remember this rule, pick the smaller of the two. So on the bottom it's t squared and on the top it's t cubed. I would always choose, and you must do it to both or it's algebraically not going to work out. Now if I do this fella, that guy gets you 4t plus 2 over infinity. And this guy gets you 3 minus 1. Oops, jumped ahead there. That's a t for the time being. And this fella is going to be a t. And now when I do brute force, 4 lots of infinity are infinity plus 2 over infinity. That's the top. 3 take away 1 over infinity. Infinity plus 0 over 3 take away 0. That's infinity is left on the top, 3 on the bottom. Uh-oh, infinity. Which means that the limit to this particular expression is infinity, right? It's an infinitely large answer. Do you remember those questions from a way back in Calc 1? I get at least one nod and a couple of nods. Okay, it's better than nothing. So what's the third method? It's got a funny name. Does anybody remember when they did limits that they showed you later on a third technique with a funny name?
Is it L'Hopital's rule?
Yes, it is. Or as I like to call it, L'Hospital. But you're right, I believe it is L'Hopital. Because I think he's Belgian. And evidently when you're Belgian, you don't always say all the syllables. Now, when are you going to use L'Hopital? I suggest that you use L'Hopital whenever you come across pretty much anything that's not a power. So what do I mean? For instance, e to the t is not a power of t, right? Now, according to L'Hopital, you can find the limit by taking the top and differentiating it, and taking the bottom and differentiating it. And if you find the limit is t tends to infinity of this, it's the same answer as that. Now, one of the things that very often happens with L'Hopital, so we normally stick a little L above the equals, is that you don't always get what you want the first time. If I plug infinity in here, would you agree that these just become infinity on top, infinity in the bottom, and who knows, I'm nowhere. But if you do it a second time, sometimes even a third time, that's the top guy derivative. This is the bottom guy derivative. Do you see I get a cancel? And what am I left with? I'm left with a fifth. So the three techniques are brute force, just plug in infinity and hope you get lucky. Divide top and bottom by t squared or t cubed, something like that, and get your answer that way. And lastly, use L'Hopital. Technically speaking, you can use L'Hopital for all of them, but it's quite messy if you have to do it 7 times in a row. You know, you can imagine t to the 7 plus something and t to, you know, big ugly things. It's not practical to do that. So let's return to the question that seems ages ago we got to, which was this fella. would you agree this one is a baby one and it's brute force? Just plug in infinity. So what am I going to get? Negative 10 over infinity plus 10. But that's basically 0 plus 10. So it's 10. So we can now say that this particular integral converges to 10. Now, this is not a proof, but it's the closest I'm going to get to convincing you that this is true. So I'm going to go into y equals, and I'm going to put the function 10 divided by x squared. I'm going to go to my window, and I'm going to start at 1, and I'm going to finish at 1,000. And then I'm going to go zoom 0 and zoom to fit. And I've broken it. Oh, maybe I haven't broken it. I'll just make it 100. And I'm going to do my window from negative 0.2 to 1. And let's see if that does it. Where are you hiding? Where are you hiding? I get something weird going on here. I'm trying to see what I've done that could possibly. Oh, darn it, in space. I'm getting bad. Okay. Here we go. There it is. Right. If you look really, really carefully, can you see the function drops to almost nothing really quickly? Now, if I go to second calc and I go to number 7, integrate, and it tells me the lower limit, which is 1, and the upper limit, which is 100. If I hit enter, it fills the thing up and it tells me that the answer is 9.9. Now, can you see that if I went to 1,000, it'd probably be 9.99, and if I went to 1 to 1 billion, it would be 9.9998. Can you imagine that if you just kept on going, it just gets closer and closer to being 10? I don't know how convincing that argument was. I think my graphs wasn't great, but you can't win them all. Have I convinced you then that 10 works? Right, this process does what it says it does. So let's try another one. Let's do an integral from, oh, who cares, 2 to infinity. And let's do that one. So that's going to be the limit as t tends to infinity of the integral from 2 to t of this fellow. What do you get if you integrate 4 over x plus 1? Don't overthink it, it's pretty straightforward. 4 over x plus 1.
For the natural log of x plus 1.
Agreed. Which means that we're going to get the limit as t tends to infinity of 4 natural logs of t plus 1 take away 4 the natural log of 3. Now in this question, I can do brute force. 4 times the natural log of infinity take away 4 times the natural log of 3. You know, if you get the natural log of an infinitely big number, isn't the answer still infinity? So isn't 4 infinities infinity? Do you think taking away 4 natural log of 3 is going to hurt infinity? Not really, right? And so the answer is infinity, which means that we will say that this particular integral diverges. If you wanted to be more specific, you could say it diverges to infinity. But normally we don't bother with why it diverges. It's enough to say it diverges and call it good. And the reason why it's just more helpful to just say the thing diverges, although a lot of the times it's because the area under the curve is infinitely big, that's what it's telling us, is that there are some special functions that, here's an example of one. And infinity is a kind of hard thing to get your head around. But can you imagine that we integrated sine x to infinity? So in other words, I'm looking for the integral, right, that particular improper integral. I'm going to do the answer without doing any calculus. I'm going to try and just use common sense. Can you imagine that you're traveling along, stopping at various places? For instance, if I stopped here, wouldn't the integral be 1? It'd be 0. Because isn't this bit cancelling that and it'd be 0? On the other hand, if I stopped, say, here, couldn't the answer quite easily be 1? But if I waited a little bit longer and stopped here, couldn't it be 1.2? And then I'd get to here and it might be 2. And then, oh, wait a minute, if you start doing this, doesn't it start going down again? So your question is, what would the area under this curve look like if you went to infinity? And isn't the answer, it's not any one particular number? Couldn't it be anywhere between 0 and 2? And for that reason, it diverges. Diverges doesn't just mean that the area under the curve is infinity. Divergence is a catch-all phrase for it ain't a number, ain't one specific number, right? It doesn't have a fixed value that we can write down. So a sine x is a good example of a different kind of it diverges. Let's try this fella. Gut feeling. Do you think this is going to converge to a number, or do you think it might just diverge? What's your gut feeling? No? No gut feelings?
I think it might converge.
Okay, it may. Because if I sketched it, it would look something like that. Right? So it does get smaller. So yeah, it may. Let's find out. Sometimes it does and sometimes it doesn't. So it's going to be the limit as t tends to infinity of the integral from 1 to infinity. And I'm going to call this guy that one, because that saves me a line of working, doesn't it? Remember earlier we did a similar question. Don't you do that so we can use the power rule on it? And so what we've now got is the limit as t tends to infinity. Add 1 to the power and divide by the new power. That's why that's now 20. And I forgot, that should be a t. And I'm using style points. And now we are going to work on this fella. That fella. Take away that fella. Brute force is quite common, at least in the ones I've been doing. You agree? Isn't this one you could just do brute force on? Okay. So 20 times the square root of infinity, take away 20. That's essentially what you're going to get. Square root of infinity is infinite. 20 infinities is still infinite. Taking away 20 from infinity is not going to do you any good. This one diverges. So you might say, why does this one not make it? Whereas one of the earlier ones, which looked very, very similar to it, the one I tried to draw a picture of, but it was really hard to see. Why did this one make it and this one not? It's all to do with how quickly it hits the x-axis. See, if you get small, but you take your time doing it, the area under that curve could be infinitely big. But if you get small really quickly, right, and so there's almost nothing left, then in those situations, the area under the curve can be and does equal a finite number. And have I at least convinced you in the math world that it's possible for that to be true? Because there's a